Hey everyone, I hope that you had a good fall break. Today we are going to talk about the Bohr model of the atom as well as quantum numbers. Last week we talked about how energy is quantized, and we talked about that there were three main observations involving light and matter that led to the quantum theory of energy. They were blackbody radiation, the photoelectric effect, and the atomic line spectra. Today we'll talk about the atomic line spectra. In an atomic line spectra, we see different distinct wavelengths of light that are emitted from that are produced from excited gas molecules. We know that sunlight is composed of white light, which is a continuous spectrum of all wavelengths of visible light. However, if we have gaseous atoms, these produce specific line spectra at specific wavelengths instead of a continuous spectrum. You'll see the spectrum down here. This, I believe, is helium, and if helium is excited and we are able to view it through a slit and separate the wavelengths of light, we see that it gives us four distinct lines. Each element has a unique emission spectrum, and it can be used to identify different chemicals and different elements present. This is a technique that is used to identify the different elements present in stars in the solar system. The observation of atomic line spectra led Bohr to start to develop a new model for the hydrogen atom. The hydrogen atom, he said, has only certain energy levels, which he referred to as stationary states. The higher the energy level, the farther the orbit is from the nucleus. When a hydrogen atom is in the first orbit, the atom is in its lowest energy state, which is referred to as a ground state. The atom can change from the stationary state only by absorbing or emitting a photon. Recall that absorption is when energy is added, and emission is when energy is released. So in this figure, we see that the energy of the photon comes in and it promotes the electron from the first energy level, which is shown by this small one here, E1, to the second energy level, and that's absorption. When emission occurs, an electron that's in an outer energy level that had been excited gives off energy and returns to the lower ground energy state. Anytime for hydrogen, an electron is in an orbit higher than n is equal to 1, right, which would be the first energy level, we say that the atom of hydrogen is in an excited state. The Bohr model of the atom helped to define the atomic line spectra. What we were able to see that there were only these unique transitions from specific energy levels that gave us specific wavelengths of light. The one that is most commonly seen for hydrogen is the Balmer series because it has wavelengths of light that are visible in the visible spectrum. He was able to correlate these using this, which is referred to as the Rydberg equation, to the different energy levels and the absorption and the emission of specific packets of energy. What this allowed us to find was that energy was behaving as a quantum of energy, which told us that energy can also behave as particles. As I said, as an atom changes its energy state by emitting or absorbing one or more quanta of energy. Over here, we can see absorption, whether it's the transition from a lower energy state to a higher energy state, going from the ground state as n is equal to 1 up to 2, 3, 4, 5. This requires absorption of a different quanta of energy in each case. In emission, we have a transition from an excited state to a lower energy state. We say that energy is emitted. This is the energy of a photon. We can see this is equal to h nu. This told us that energy could behave like a particle. All of these discoveries help us to explain the different colors that we see of light. These are related to the amount of energy absorbed or emitted and the distance that an electron travels. Large transitions between energy levels will emit or absorb light with higher energy and shorter wavelengths. whereas smaller transitions will have lower energies. We know that each element has a characteristic line spectra due to the difference in energy levels and the number of electrons in each atom. Unfortunately, Bohr's model of the atom broke down after we talked about the hydrogen atom. However, based on these three experiments, the black body radiation, the photoelectric effect, and the atomic line spectra, scientists came up with the idea that light and energy have wave-particle duality. It says that light energy is not continuous. It consists of individual steps. Photons are light particles that contain a packet of energy and that can only be in certain allowable frequencies, right? And this led us to believe that we have wave-particle duality. Light can behave as a light wave, and it can also behave as a particle. What this further led to was the wave-particle duality of both matter and energy. So the scientists said, if light can behave as a particle in a wave, maybe all other things can behave as a light and a wave. Or not as a light and a wave, I'm sorry, as a particle and a wave. This led ultimately to the theory of relativity by Einstein, which said that matter and energy are alternate forms of the same entity. We're not going to get into details about the theory of relativity, but basically what we were saying is that all matter can exhibit properties of both particles and waves. However, the wavelengths of really large objects, such as a baseball or something, if we look down here at this table, all right, because its mass is so large, all right, the wavelength of a baseball is extremely small. It's 1 × 10 to the -34th. Right, so we don't have to worry about the wavelength of a baseball because it is so small. However, an electron has a very small mass, and thus it has a wavelength that can be measured by scientific instruments. So we know that electrons have wave-like motion and therefore have only certain allowable frequencies and energies. This led us to the idea that an electron behaves both as a particle and as a wave and is part of the foundation of quantum mechanics. As I said earlier, the Bohr's theory worked well for the hydrogen atom, but it was unable to explain the behavior of atoms with more than one electron. We learned that electrons behave like particles in some circumstances and waves in other circumstances. And therefore, we needed to think about both of these things when we're describing where an electron is. This led to Heisenberg's uncertainty principle, which states that it is not possible to know both the position and the momentum of a moving particle at the same time. If we know the speed very accurately, we do not know the position. If we know the position of an electron, we do not know the speed very well. I will post this video outside of these lecture notes. This is a very good video that kind of summarizes the quantum mechanics of the electron and how we moved from the photoelectric effect and atomic line spectra into our modern view of quantum mechanics. It does a better job, I think, of explaining some of the wave-particle duality principles than I just did. All right, so now we are moving into our quantum mechanical model of the hydrogen atom. The Schrödinger equation is shown above here. We do not need to memorize the Schrödinger equation. I'm just showing it here to talk about how we use the Schrödinger equation. The Schrödinger equation allows us to solve for the energy states associated with a particular atomic orbital. And the solutions to the Schrödinger equation are called wave functions. The square of a wave function defines an atomic orbital. which is the space around the nucleus of an atom where the probability of finding an electron is high. Recall with the Heisenberg uncertainty principle, we now are never able to 100% accurately know the speed and position of an electron. So the Schrodinger equation allows us to predict the probability of finding an electron in a particular area. Quantum numbers are the solution to the Schrodinger equation, and they are used to describe the characteristics of an electron and the distribution of electron density in an atom. In the Bohr model, there was only one quantum number, which was n. However, we have a total of 4 quantum numbers. The first 3 quantum numbers, n, l, and m, specify the particular orbital that an electron can be in, and the 4th quantum number, m sub s, specifies how many electrons can occupy that orbital. What is extremely important is that no 2 electrons in an atom can have the same 4 quantum numbers. All right, we're going to go into more detail about all 4 of these quantum numbers now. So it's important to remember that an atomic orbital is specified by 3 quantum numbers. Remember, an atomic orbital is the probable area of where we're going to find an electron. The principal quantum number is referred to as n. This one's really easy. This is a positive integer. It can be anything. It can be 1, 2, 3, etc. We typically refer to this as the energy level or the shell of where the electron can be, or of our orbital. This indicates the relative size of the orbital and its distance from the nucleus. Remember when we saw those circular patterns for the hydrogen atom? N was equal to 1, 2, 3, 4. Okay, these are their shells. The angular momentum quantum number is given the symbol L, and it can be an integer from 0 all the way up to n minus 1. The value of L indicates the shape of an orbital, and this represents the sublevels of an atom's energy level. So if I have a principal quantum number equal to 1, so n is equal to 1, the only value I can have for L is 0. If I have a principal quantum number of 2, I can have values of L for be 1 or 0, because I can only go up to n minus 1. The third quantum number is the magnetic quantum number, m sub L, which can be an integer with values based on L. It can go from negative L to positive L. And this indicates the spatial orientation of an orbital. And the m sub L quantum number represents a specific orbital in an atom. The last quantum number is our electron spin quantum number, m sub s. This describes the spin on the electron in the orbital. Now this is an easy one. It can either be plus 1/2 or minus 1/2. Remember that each electron in an atom is described completely by a set of 4 quantum numbers. So if I have 4 electrons, I have 4 sets of 4 quantum numbers, one to describe each electron. The Pauli exclusion principle says that no 2 electrons in the same atom can have the same 4 quantum numbers. What that means is that if an atomic orbital can hold a maximum of 2 electrons, and that they have to have opposite spins. One is going to have an m sub s value of positive 1/2, and one is going to have an m sub s value as negative 1/2. If you're used to seeing atomic orbitals, some of you may have seen this in the past, you'll see an orbital by a line, and one electron is going to be pointing up, and one electron is going to be pointing down. Sorry, my pen didn't work with this presentation mode, so I have to use the mouse to do it. All right, so this line is going to represent our atomic orbital. this is going to represent an electron with a spin of positive 1/2, and this would represent an electron with a spin of negative 1/2. We want to talk about what types of shapes atomic orbitals can take and how that is related to our L values. Atomic orbitals don't have well-defined shapes because they are represented by the wave function, all right? But what we can do is we can visualize them as having specific shapes, because the probability of finding an electron in a specific area has been solved by the Schrodinger equation. If we have s orbitals, this is where L is equal to 0. When L is equal to 0, m sub L is equal to 0. And there is only one orbital. All s orbitals are spherical in shape, but they're going to be different in size. All right, the size of the sphere increases as n increases. You'll see here that I have the 1s orbital, okay, which is smaller in size than the 2s orbital and the 3s orbital. In each of these cases, L is equal to 0. In this case, n would be equal to 1. In this case, n would be equal to 2, and n would be equal to 3 in this case. But L is equal to 0 for all s orbitals. For all p orbitals, L is equal to 1. If L is equal to 1, m sub L can be equal to -1, 0, and +1. I can have a total of 3 orbitals. One is the -1, one is 0, and one is +1. Our p-shaped orbitals have these dumbbell-shaped or with 2 different lobes, right? And an electron in the p orbital can occupy both lobes. We also have a node in a p orbital, which is an area with 0 probability of finding an electron. When we are at the same energy level, that's the n energy level, all right? So n is equal to 2 or 3. These orbitals are referred to as degenerate, meaning that they all have the same energy. The p orbitals also increase in size as the n value increases. All right, so this figure shows the 3 different p orbitals. We refer to these often as pz, px, and py. These are related to the -1, 0, and 1 m sub L quantum numbers. So there's 3 orientations which come from my 3 different m sub L quantum numbers. Our d orbitals occur when L is equal to 2. And when L is equal to 2, I can have m sub L values of -2, -1, 0, +1, and +2. This gives me a total of 5 orbitals. We know that an electron in the d orbital can occupy all of the lobes of a d orbital. And at a specific energy level, just with our p orbitals, these orbitals are degenerate, which means they all have the same energy. All right, so if you look here at our d orbitals, this is where L is equal to 2. M sub L can be equal to -2, -1, 0, 1, and 2, which relate to my 5 orbitals. 1, 2, 3, 4, and 5 different orbitals. Finally, we have our f orbitals, which is where L is equal to 3. And if L is equal to 3, I can have an m sub L value of -3, -2, -1, 0, +1, +2, and +3, which gives me a total of 7 orbitals. These have very complex shapes and are difficult to represent, so we aren't going to talk about in more detail about f orbitals. All right. So we talked about all these different orbitals. We talked about how the different quantum numbers were related to the shape of the orbital. We are often going to see orbitals written as below. We're going to see them as 1s. 2p, 3d. Okay, those are all examples of what we're going to see. The n value of our quantum number is the 1, is the number in front. This is where n is equal to 1. All right. The s, we know if it is an s orbital, L is equal to 0. That's just something that we have to know. S is where L is equal to 0. P is where L is equal to 1. D is where L is equal to 2. Okay, that's just something that we are going to have to memorize. All right. These describe a specific orbital for an electron. So what would be the n and L values for a 4p orbital? All right, if we break this down, we have 4p. So n is equal to 4. Okay, the n value. And L, since it's a p orbital, L is equal to 1. All right, that is how we can break down our different quantum numbers. All right, let's look at a couple more examples of quantum numbers to try to kind of sort out some of it, because I understand that there's a lot of if and then and this and what is allowed and what is not allowed. All right, so for the first one here, it says how many orbitals are allowed for n is equal to 3? Remember, when n is equal to 3, L can be 1, can be 1, 2, or 1 or 2. Because we can go all the way up to n minus 1. If L is equal to 1, we know m sub L is equal to 0. That's one orbital. Oh, and L, I'm sorry, can also be equal to 0. If m sub L is equal to 1, or if L is equal to 1, m sub L is going to be equal to 0. That's going to give us, let's start over. I don't like this. I went the wrong direction here. All right, sorry. If n is equal to 3, L can be equal to 2, 1, or 0. Okay, that gives my 3 different ones, right? This is going to give me S, P, and D orbitals, or shapes, I'm sorry, not orbitals. Okay, for an S, all right, for the L is equal to 0, m sub L is equal to 0. When L is equal to 1, m sub L is equal to -1, 0, and 1. And when L is equal to 2, m sub L is equal to -2, -1, 0, 1, and 2. These m sub L values are my orbitals. So I count up however many m sub L values I have. All right, I have 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have 9 orbitals in the n is equal to 3 category. Wow, I'm really bad at that, sorry. And I left them bolded for you. All right, so now, which of the following sets of quantum numbers can correctly represent a 3p orbital? Remember that the first number is where n is equal to 3. Okay, that's that one there. And if we have a p, we know that L is equal to 1. All right, I had 2 choices then. all right? If n is equal to 3 and L is equal to 1. This choice, where n is equal to 3 and L is equal to 1, and this choice. However, this top choice is incorrect because if L is equal to 1, M sub L cannot be equal to 2. If L is equal to 1, M sub L can be -1, 0, and 1. Therefore, D is the correct answer here. All right, and then finally, which of the following combinations of quantum numbers is not allowed? So in order to answer a question like this, we need to go through each of them and decide, is this set of quantum numbers allowed based on the rules that we have? In A, n is equal to 3, L is equal to 2. Is that allowed? Yes, because L can be all the way up to n minus 1. All right, so that's good. And then if L is equal to 2, M sub L can be equal to -2, -1, 0, 1, or 2. So this one is good. In the next example, in B, if n is equal to 3, L is not able to be equal to 3 because we can only go up to, L can be equal, is an integer up to 0 up to n minus 1. All right, so if n is equal to 3, L can only, in this case, be equal to 0, 1, and 2. So this is not an allowed set of quantum numbers. Let's take a look at C just to make sure we understand why that one is allowed. If n is equal to 3, we know that L can be equal to 1, 0, 1, or 2, which is acceptable. L can be equal to 2. And if L is equal to 2, we know that M sub L can be equal to -2, -1, 0, 1, or 2. So this set is allowed. And then finally, if n is equal to 3, L can be equal to 0. That would be a 3s orbital. And M sub L can be equal to 0 as well. So that is a valid quantum set of quantum numbers. All right, I have 2 slides after this, which just summarize each of the things that we talked about, okay? This slide summarizes the different quantum numbers. We have the angular momentum quantum number, which is L, all right, and how that relates to the sublevel or the shape of the orbital. Remember, if L is equal to 0, it has an S shape, and we can only have one orbital, where M sub L is equal to 0. If L is equal to 1, we have a P or dumbbell shape. We can have 3 P orbitals, where M sub L is -1, 0, and +1. If we have an L value of 2, we can have a sublevel up to, or our sublevel is D, and this takes a clover shape. And in this case, we can have 5 orbitals. And then if our L value or angular momentum value is equal to 3, this is the F shape, and these are complex multi-lobed orbitals, but we can have 7 of them, okay? -3, -2, -1, 0, +1, +2, and +3. And this slide here also gives you an explanation of some of the different angular momentum numbers along with the principal quantum numbers for each of the different values of n. It shows you, for instance, if n is 1, L is 0, which is an S, my magnetic quantum number, M, that should say M sub L. All right, and how many orbitals are associated with that, okay? To get the total number of orbitals in a principal quantum number, you would add each of the values of the orbitals in each of the sublevels. So this would be the D. So in 2, we can have, in the 2, we can have 4. All right, and in the principal quantum number of 3, the energy level 3, remember we answered this question earlier, we can have 9, and so on and so forth. Okay. Please remember to take the short quiz that talks about the definition of each of these quantum numbers, and then you should be able to get started on your homework for this particular week. I hope you guys had a great fall break, and I will see you either on Friday or next week. Thanks.